Bit 00 solid. The floor under your feet, the air in your lungs, the light reaching your eyes right now. All of it behaves. Drop something and it falls. Flick a switch and the circuit closes. A trillion tiny predictions confirmed every second of your life, so quietly you have stopped noticing. You trust this the way you trust your own heartbeat, not because you checked, because it never failed. The equations work. They predict. They land. And the world built on top of them runs fine. But here is what is strange. Not that the rules work. They work beautifully. That is not the problem. The problem is what happens when you ask why. Why these rules? Why these numbers? Why does the machine run at all? Because the moment you ask, physics does not give you a deeper answer. It gives you silence. And that silence is not at the edges, where you would expect the map to go blank. It is in the middle. So let us go there. Let us start with the part of the map we thought was most complete. Bit 01. For 70 years, the expansion of the universe was the most settled fact in cosmology. Not controversial, not debated, settled. Edwin Hubble measured it in 1929. He looked at distant galaxies and found that every one of them was moving away from us. The further it sat, the faster it receded. Space itself was stretching, like a rubber band being pulled from both ends, carrying everything on it further apart without anything sliding across the surface. And the explanation was clean. Something had thrown all of it outward, the Big Bang, and gravity was pulling it back. Think of tossing a ball straight up. It decelerates from the second it leaves your hand. Maybe it falls back. Maybe it drifts up forever, slower and slower. Either way, gravity is the brake. That was the picture, and the picture held. The model predicted a faint glow in the sky, a remnant of the first light released when the universe cooled enough to become transparent. We looked for it and found it exactly where the math said it would be. It predicted how much hydrogen and helium the first 3 minutes should have produced, and the measured ratio matched. It predicted the way galaxy clusters would scatter across the sky, and they scattered that way. 70 years of predictions. Everyone confirmed. Gravity was winning. The expansion was decelerating. Nobody questioned this. It was one of the few things in cosmology you could call finished. So when 3 teams in the late 1990s set out to measure the exact rate of that deceleration, it was not an adventure. It was a formality. Saul Perlmutter at Berkeley, Brian Schmidt and Adam Rees on the other side of the planet, both using a type of exploding star that always detonates at roughly the same brightness, which lets you calculate distance by how dim it looks. Dying stars as rulers. Both teams stretched those rulers across the cosmos and expected the most boring possible result. A cleaner decimal on a closed question. Bit 02. The question was not closed. Perlmutter's team ran the data and the curve pointed the wrong way. They spent months looking for a calibration error. They reprocessed the observations. They reanalyzed the light curves. The result did not change. Across the Pacific, Schmidt and Rees hit the same wall independently. Different dataset, different pipeline, same answer. The expansion of the universe was not decelerating. It was accelerating. That is a strange sentence. It is worth sitting with for a moment. Everything in the observable universe pulls on everything else through gravity. Every galaxy, every star, every atom, all of it pulling inward. And something else, something not in the model, is pushing outward harder than all of that combined. Not slightly harder, dominantly. The energy behind this acceleration accounts for roughly 68% of everything that exists. The entire visible universe, every star and planet and dust cloud you have ever seen in a photograph from a telescope, is about 5%. The rest is something that was not predicted, not described, and not detected before these results arrived. We called it dark energy, and the name is worth thinking about. It does not describe what the thing is. It describes the shape of what we do not know. A label on a blank. In the 26 years since, thousands of physicists with the most sensitive instruments the species has ever built have been trying to fill in that blank. The answer has not moved. We do not know what dark energy is. We do not know where it comes from. We do not know whether it is changing or staying the same. And that last part matters, because the fate of everything that exists depends on it. Perlmutter, Schmidt, and Rees won the Nobel Prize in 2011 for finding the acceleration. The award celebrated what they discovered. It had nothing to say about the fact that no one can explain it. Bit 03. So the thing that makes up 2/3 of the universe has no explanation. But the equations should be able to give one. That is what they were built for. General relativity tells you how energy warps the shape of space. If there is energy out there accelerating the expansion, the math should describe it. And here is what makes this strange. It does. There is a term for exactly this, and it has been sitting inside the equation since 1917. Einstein put it there himself. 2 years after finishing general relativity, he added a constant to the geometry. Think of it as a dial. He needed the universe to stay still, because everyone at the time assumed the cosmos was static and eternal. The dial held it still. Then Hubble discovered the expansion, and Einstein tore the dial out. He called it the worst mistake of his career. But 81 years later, the expansion turned out to be accelerating, and the only mathematical term that could describe the acceleration was the one Einstein had thrown away. His worst mistake became his most necessary contribution, and he was not alive to see it. Now here is where it gets worse. There is a second set of equations that also speaks to the energy of empty space, and it comes at the question from a completely different direction. Quantum field theory describes how particles and forces behave at the smallest scales. One of its predictions is that even a perfect vacuum is never truly still. Particle pairs flicker in and out of existence constantly, and their combined effect gives empty space a kind of background hum, an energy that is always there. You can calculate this energy. The calculation is straightforward, but the answer is not. The vacuum energy predicted by quantum field theory overshoots the observed value by a factor of 10 to the 120th power. Not 10 times too high, not a million. A 1 followed by 120 zeros. These two frameworks, general relativity and quantum field theory, are the two most precisely tested descriptions of nature we have. Both are trusted with technology, engineering, human lives. And when you point them at the same question, the answers they return do not just disagree. They disagree by a margin that is, itself, a larger number than most numbers in physics. One of them is wrong about this, possibly both. And the number they cannot agree on is the one that determines how everything ends. Equals 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 bit 04 equals equals equals. That is not a metaphor. The value of dark energy determines the future of the cosmos, and the future has 3 possible shapes, and they look nothing like each other. If the energy holds steady, never growing, never fading, then the expansion continues accelerating at a constant rate. Stars burn out one by one over trillions of years. Galaxies drift so far apart that the light from one can never reach another. The night sky goes dark, not because there is nothing out there, but because the photons from the nearest galaxy will never arrive. The temperature of everything drops toward absolute zero. The last structures dissolve. What is left is not darkness. It is emptiness so complete that even the word darkness stops applying. Physicists call this the Big Freeze. The universe does not end. It just forgets it was ever here. If the energy grows over time, even slightly, the picture changes. What starts as a force that pushes galaxy clusters apart becomes a force that tears things apart at every scale. First, the clusters separate, then the galaxies themselves, then solar systems, then planets, then atoms. Robert Caldwell at Dartmouth calculated in 2003 that under certain conditions, this process completes in finite time. The fabric of space-time itself comes apart. This is the Big Rip, the big. And if the energy weakens, gravity eventually catches up. The expansion slows, stops, reverses. Everything that has been flying apart for 13.8 billion years begins falling back together, compressing, heating, until the entire observable universe crushes into a volume smaller than an atom. The Big Crunch, a mirror of the beginning, 3 futures, 3 completely different endings, and we cannot distinguish between them because the number that decides which one is real is the number we cannot pin down. We know the fate of the universe depends on this value. We know the value exists. We cannot read it. And that gap between knowing a number matters and not being able to determine it is the first place where you feel the floor start to thin. But here is what bothered me when I first looked at this. Dark energy is one number. What about the rest? What about all the other numbers that physics depends on? Surely those are derived. Surely those come from somewhere solid. Bit 05, they do not. And this is where it stopped feeling like a gap in knowledge and started feeling like something structural. The standard model of particle physics is the framework that describes every known particle and 3 of the 4 fundamental forces. It predicted the Higgs boson 2 decades before anyone found it. When they found it at CERN in 2012, it was exactly where the math said it would be. This is not a rough sketch. This is the single most precisely tested framework in the history of science, and it runs on 26 numbers that it cannot generate. The masses of the quarks, the strength of the electromagnetic force, the angles at which certain particles transform into others. 26 values that determine how every atom in the universe behaves, and not a single one of them is derived from the theory. They are not predicted. They are not calculated. They are measured in laboratories and typed into the equations by hand, the way you type a password into a locked screen. The machine does not produce its own settings. It requires you to supply them. Here is what that means, and it took me a while to see why it matters. The most powerful description of reality we have does not explain its own foundation. It does not tell you why the electron has the mass it has, and not some other mass. It does not tell you why gravity is weaker than the other 3 forces by a factor of 10 to the 36th, a ratio so extreme that nothing else in physics comes close to it. It does not tell you why matter comes in 3 generations instead of 2 or 5 or 1. It takes 26 numbers from nature, returns extraordinary predictions, and never once tells you where the numbers came from. So maybe they are arbitrary. Maybe nature could have picked any values, and some kind of universe would emerge. Different chemistry, different stars, different rules, but still a universe. That is a reasonable thought. And it falls apart the moment you look at the margins. Bit 06 changed the strength of the strong nuclear force by 0.5%, and carbon cannot form inside stars. No carbon means no organic chemistry. No organic chemistry means nothing complex enough to carry information, copy itself, or evolve. Shift the gravitational constant by 1 part in 10 to the 40th, 1 digit in a number with 40 zeros, and stars burn through their hydrogen in millions of years, instead of billions. No time for planets to cool. No time for chemistry to complexify. No time for anything to crawl out of a sea. Nudge the electromagnetic force by 4% and stable atoms stop existing. No atoms, no molecules, no solids, no liquids, no surfaces. Just radiation. These are not extreme scenarios designed to make a point. These are the actual tolerances. And what makes them unsettling is not any one of them individually. It is the fact that all 26 values sit inside their windows simultaneously. The probability question here is genuinely hard to formulate. Because to talk about probability, you need to know the distribution the numbers were drawn from, and we do not know that. But what we can say is this. The space of values that permits a universe with structure is vanishingly small compared to the space that does not. Miss 1 value and there are no atoms. Miss 2 and there is no light. Miss 3 and space does not hold a stable geometry. Every margin met. every window hit, and no equation can tell you why any of them have the values they do, let alone why all of them line up at once. Physics has a name for this: fine-tuning. But here is the thing about that name. It is not an explanation. It is an admission that you notice something you cannot account for. You saw the locks. You saw that every key fits. And you have no idea who cut the keys or why they work. Bit 07. One physicist followed this thread further than most, and it took him somewhere he did not expect to go. Fred Hoyle was one of the dominant figures of 20th century astrophysics. He helped build the theory of how stars forge heavy elements in their cores. He was also an outspoken atheist, public about it, fierce about it, the kind of man who did not flinch from difficult conclusions because he had spent a career chasing them. In the early 1950s, Hoyle ran into a problem with carbon. Stars build heavier elements step by step, fusing hydrogen into helium, helium into heavier nuclei. Carbon is a crucial step on this ladder. But when Hoyle worked through the nuclear physics, the numbers did not add up. The intermediate step, beryllium, decayed too quickly for the next reaction to happen at a meaningful rate. There was not enough time in the life of a star for the process to produce the amount of carbon we see in the universe. Carbon should be rare. It is not. You are made of it. So Hoyle did something that, in hindsight, is one of the most remarkable moves in the history of physics. He predicted that the carbon-12 nucleus must have an excited energy state at exactly 7.65 million electron volts. Not roughly, exactly. Because without this specific resonance, the reaction rate could not spike high enough to produce carbon in quantity. He was not deriving this from theory. He was deriving it from existence. Carbon exists, therefore the resonance must exist. The logic was clean. Find it. William Fowler's group at Caltech tested the prediction within months. The state was there. At 7.6 mega electron volts, exactly where Hoyle said it would be. A number pulled not from the equations but from the fact that the universe contains carbon, confirmed in a laboratory. Hoyle never quite recovered from the implication. He wrote afterward that a common-sense reading of the data suggests that someone has monkeyed with the physics. This was not a man reaching for a comforting answer. This was an atheist staring at a result he had predicted himself, confirmed himself, and could not explain through any mechanism he knew. The data had walked him to a door he did not want to open. And the question behind that door is the one physics has been circling ever since. If the numbers are not derived, and the margins are this tight, and every key fits every lock, then who cut the keys? Or is that even the right question? Bit 08. Physics has two answers to that question. Neither one works, but they are the only ones on the table, and it is worth understanding why they fail, because the failure is what drives you deeper. The first is called the anthropic principle. It says, the constants have the values they have because if they did not, no one would be here to notice. Carbon exists because the Hoyle state exists, and we can only observe a universe that contains carbon because we are made of carbon. This sounds like it closes the loop until you realize it does not explain anything. It does not tell you why the numbers have these values. It tells you why you can only observe these values. That is a different statement. Saying the combination works because otherwise nobody would complain is not a mechanism. It is a shrug dressed as an insight. The second answer is the multiverse. It proposes that there is not one universe but an enormous number of them, possibly infinite, each with different constants. In most of them, the numbers are wrong and nothing forms. In a tiny fraction, the numbers line up, and those are the ones that produce observers. We are in one of those. It is a clean solution on paper. The problem is that no instrument can detect another universe. No signal crosses the boundary. No experiment can confirm it or rule it out. A framework that explains all possible outcomes and predicts none of them is, in scientific terms, not a framework. It is a story. So here we are. The numbers are not derived. The margins are impossibly tight. The two proposed explanations are a tautology and an untestable hypothesis. At the largest scales, the map has gone quiet, and when the large scale gives you nothing, there is one place left to go: down, to the smallest thing you can observe directly, to a single particle, a barrier with 2 slits, and a detector. This is where physics expected to find solid ground. What it found instead was something that still, after 100 years, has no agreed-upon explanation. Bit 09. Take a barrier with 2 narrow slits. Fire particles at it, one at a time, and record where each one lands on a screen behind the barrier. If particles are little bullets, you would expect 2 clusters, one behind each slit. What you get instead is an interference pattern. Alternating bands of light and dark. The kind of pattern that only appears when waves overlap, reinforcing in some places and cancelling in others. A single particle, fired alone, with no other particle anywhere near it, lands in a spot consistent with a wave pattern. Do it 1,000 times, and the pattern builds up, dot by dot, on the screen. Akira Tonomura captured this in 1989, firing single electrons one at a time and recording each hit. If you watch the footage, the first few hits look random. Scattered dots with no structure, nothing to suggest a pattern. But as the count climbs into the hundreds and then thousands, the bands appear. Light and dark stripes, assembling themselves out of what looked like chaos. Order that was not put there by anything visible. Each electron alone, with nothing to interfere with, landing in a spot that, over time, contributes to a structure that should not be there if the particle went through only one slit. That is already strange. But the real problem comes next. Put a detector at one of the slits. Find out which slit each particle goes through. The moment you do this, the interference pattern vanishes. The particle goes through one slit. It lands in one cluster. It behaves like a bullet, not a wave. The act of extracting witch path information physically changes the outcome. This has been confirmed thousands of times since Thomas Young first demonstrated interference with light in 1801. Johnson did it with electrons in 1961. Tonomura did it with single electrons in 1989. The result is not ambiguous, and it is not contested. When witch path information is available, the particle behaves one way. When it is not, the particle behaves another way. Reality at the smallest scale does not seem to settle into a definite state until something interacts with it in a way that records the outcome. You might think this is just a mechanical problem. The detector is a physical object. Maybe it bumps the particle. Maybe it injects energy. Maybe the interference pattern disappears for a boring reason. You poke something small with something large. That is a reasonable objection, and it was taken apart by a single experiment. Bit 10. There is a reasonable objection to everything we just described, and it needs to be addressed before we go further. Maybe the detector physically bumps the particle. Maybe the interference pattern vanishes for a boring mechanical reason. If so, then a choice made after the particle has already passed through the slits should change nothing. The event is over. Whatever happened, happened. John Archibald Wheeler proposed exactly this test in 1978. He called it the delayed choice experiment. It sat on paper for decades. Then, in 2007, Vincent Jacques and his team built it and ran it. The result matched Wheeler's prediction and broke common sense. When the experimenters chose to record path information after the particle had passed, the particle behaved as though it had gone through one slit. When they chose not to record, it behaved as though it had gone through both. The decision came after the event, and the event matched the decision. This is not a fringe interpretation of noisy data. It is a clean, published, replicated result that no working physicist disputes. And what it says carefully is this: you cannot assign a definite history to the particle before the measurement is complete. The past of the particle is not fixed independently of what you choose to do in the present. This is not the same as saying the future controls the past, though it is easy to read it that way. What the experiment actually shows is subtler and, in some ways, more disturbing. The question, what did the particle do, has no answer until the entire experimental context, including the final measurement choice, is settled. The history is not rewritten. It was never written. It does not exist as a fact until the measurement makes it one. This breaks something that runs deeper than any particular theory. It breaks the assumption that events have definite outcomes, whether or not anyone records them. It breaks the assumption that the past is fixed. And physics has been trying to explain this for 100 years. What it has produced in that time is not an answer. It is a catalog. Bit 11. There are more than 15 competing interpretations of quantum mechanics. Each one offers a different picture of what is happening when a particle passes through two slits. Each one is mathematically consistent, and not one of them can be distinguished from the others by experiment. The Copenhagen interpretation says the particle does not have a definite state until measured. It exists in a superposition, all possibilities at once, and the act of measurement collapses the superposition into a single result. Reality, under this view, does not settle until something forces it to. The many worlds interpretation says the collapse never happens. Every possible outcome is realized. The universe splits. When the particle hits the screen, one branch of reality sees it land here and another branch sees it land there. Both are equally real. Both continue. The branching happens every time a quantum event has multiple possible outcomes, which means it is happening constantly, producing a number of parallel realities so vast it dwarfs every number in astronomy. Cubism says quantum mechanics does not describe the world at all. It describes the expectations of an observer. The math is about what you can predict, not about what is out there. Reality exists, but the formalism is a tool for navigating it, not a mirror of it. These are 3 of more than 15, and here is what should stay with you. They all give the same predictions, every single one. There is no measurement, no experiment, no observation that can tell them apart. The most precisely tested theory in the history of science cannot tell you whether reality collapses, branches, or is simply not the kind of thing the theory describes. It tells you what will happen with extraordinary accuracy and has nothing to say about what is happening or why. You would think that after 100 years, someone would have found a way to at least narrow the field. In 1964, someone did. Not by choosing an interpretation, but by asking reality a simpler question. A question with only 2 possible answers. Bit 12. John Bell was a physicist at CERN, quiet and precise, not the kind of person who made dramatic claims. In 1964, he proved a theorem that did something none of the interpretations could do. It tested reality itself. The theorem is built on 2 assumptions that seem so obvious they barely feel like assumptions. The first is locality. Nothing affects anything else instantly across a distance. If you flip a coin in one city, it does not change the result of a coin flip in another. The second is realism. Objects have definite properties whether or not anyone measures them. The moon is there when nobody looks. Bell showed that if both of these are true, then the correlations between certain pairs of entangled particles cannot exceed a specific limit. Stay below the limit, and the world is local and real. Cross it, and at least one of the 2 assumptions fails. In 1982, Alain Aspect set up the experiment in Paris. He created pairs of entangled photons, sent them in opposite directions, and measured the correlations. They crossed the limit. The world is not both local and real. The experiment has been repeated and refined continuously since. Every loophole that critics identified was closed in successive versions. In 2015, a team in Delft ran a version designed to shut every remaining gap in a single run. The result held. In 2017, a Chinese team tested entanglement across 1,200 kilometers using the satellite Messius. Same result. The correlations are there. They violate Bell's inequality, and that means at least one of our 2 most basic assumptions about reality does not hold. Either things can influence each other instantly across any distance, which means space does not enforce separation the way we thought. Or objects do not have definite properties until measured, which means the world is not fully there when no one is looking. At least one of these has to go. And the honest answer, the one that keeps physicists up at night, is that we do not know which. What we do know is that one of the two pillars that classical physics was built on is broken. And once you accept that, the next question becomes unavoidable. What about the other things we take for granted? What about time? Bit 13. You feel time more directly than you feel anything else in physics. It is more immediate than gravity, more constant than light. Yesterday is behind you. Tomorrow is ahead. Coffee cools. Eggs break. You get older, never younger. Time flows in one direction, and the flow is so fundamental to your experience that questioning it feels absurd. Every memory you have, every plan you make, every cause and every effect, all of it depends on time having a direction. Without it, the concepts of before and after collapse. Without it, nothing happens, because happening requires sequence, and sequence requires an arrow. But here is something that almost never comes up outside a physics department. The direction of time is not in the equations. Take every fundamental law we have, Newton's laws, Maxwell's equations, the Schrödinger equation, Einstein's field equations. Replace the variable t with negative t. Run the math backward. Every one of these equations still works. A ball falling to the ground and a ball rising from the ground into a waiting hand are equally valid solutions. An egg unscrambling and climbing back into a shell is permitted by every fundamental equation in physics. The laws do not forbid it. They do not even notice the difference. And yet, it never happens. Coffee does not reheat itself. Eggs do not unscramble. Glass does not leap from the floor onto the table. The universe moves in one direction, always forward, always toward greater disorder, and nothing in the fundamental math says it has to. The arrow of time, the thing that separates memory from anticipation, cause from effect, past from future, is not a fundamental law. It is something else, something that enters physics not through the equations but through the conditions. And the standard explanation for what that something else is, the one you will find in most textbooks, is not as solid as it looks. Bit 14. The usual answer is entropy. The second law of thermodynamics says that entropy, the measure of disorder in a system, increases over time. Hot things cool. Organized structures fall apart. Rooms get messy. This is why time seems to have a direction. The universe moves from order to disorder, and we ride that wave and call it the passage of time. That sounds like an explanation until you look at what Boltzmann actually proved. Ludwig Boltzmann, the Austrian physicist who built the mathematical foundation of entropy in the late 1800s, showed that the second law is not a law in the way gravity is a law. It is a statistical tendency. Entropy increase is overwhelmingly probable, not mandatory. Picture a box full of gas. The molecules bounce around randomly. There is nothing in the laws of physics that prevents all of them from drifting to the left side of the box at the same moment, leaving the right side empty. No force forbids it. No equation blocks it. It is allowed the way a fair coin landing heads 1,000 times in a row is allowed. The rules permit it. The probability is simply so low that in the entire history of the universe it has almost certainly never happened on a macroscopic scale. But almost certainly is not the same as cannot. Unlikely and impossible are different words, and the gap between them matters here, because the entire arrow of time lives inside that gap. Because if the arrow is not the same as cannot, unlikely and impossible are different words, and the gap between them matters here, because the entire arrow of time lives inside that gap. Because if the arrow of time rests on statistics rather than on a fundamental rule, then it does not explain why time moves forward. It describes the fact that it does. It tells you what tends to happen, not why. And when you push on this, When you ask why entropy has been rising for 13.8 billion years without a single large-scale reversal, the answer is not a mechanism. It is an assumption. Entropy is rising because it started low. The universe began in a state of extraordinary order, and everything since has been a slide downhill from that starting point. The direction of time is not written into the laws of physics. It is written into the initial conditions, and the initial conditions are not explained by anything. Bit 15. This is called the past hypothesis, and it is worth understanding what it actually is. It is not a theory. It is not a derivation. It is a postulate, an assumption made because without it the direction of time has no foundation. It says, the universe started in a state of extremely low entropy. That is all. No reason offered, no mechanism described. The most basic feature of your experience, the fact that yesterday is behind you and tomorrow is ahead, depends entirely on an initial condition that physics takes as given and cannot justify. Roger Penrose, Sean Carroll, David Albert, three of the most careful thinkers working on the foundations of physics, all agree on this point. The past hypothesis is necessary. Without it, statistical mechanics has no way to account for why entropy has only gone up, and none of them can explain where it came from. Penrose went further. He asked the probability question. If the initial state of the universe had been drawn at random from all possible states, how likely is it that we would get one with entropy this low? The number he calculated requires a notation you do not normally see. 1 chance in 10 to the power of 10 to the power of 123. This is not a number you can write down. The exponent itself has an exponent, and the second exponent is 123. If you tried to write out all the zeros, one per atom, using every atom in the observable universe, you would run out of atoms before you ran out of zeros. The number is larger than the universe it came from. So here is where we stand. The direction of time depends on the initial conditions of the universe. Those conditions are not derived from any theory, and the probability that they occurred by chance is a number so large it does not fit inside the reality it describes. Time is not a fundamental feature of physics. It is a consequence of a starting point that no one can explain. One pillar gone, and that immediately raises a question about the other one. If time is not what we thought it was, what about space? Bit 16. Space feels like the most obvious thing there is. The distance between two objects is measurable, consistent, and does not change unless something physically moves. You reach out your hand and the wall is there. The gap between here and there is real. It separates things. It enforces boundaries. If something happens on one side of a room, it does not instantly affect the other side. Things have to travel. Signals take time. Influence moves at finite speed. Space is not just a container. It is a rule. It says, here is not there, and getting from one to the other costs something. In 1935, Einstein found a reason to doubt this. Working with Boris Podolsky and Nathan Rosen, he showed that if quantum mechanics was a complete theory, then measuring one particle would instantly determine the state of another particle, no matter how far apart the two were. Not after a signal traveled between them, not after any time passed. Instantly. Einstein did not present this as a discovery. He presented it as an absurdity, a proof that the theory was missing something. He called it spooky action at a distance, and the argument was clear. If quantum mechanics requires instant connections across space, then quantum mechanics must be incomplete. There must be hidden variables, local information that each particle carries from the moment of separation, that explain the correlations without anything needing to violate the speed of light. Einstein was certain about this. Space enforces separation. What happens here cannot instantly affect what happens there. For nearly 50 years, his argument stood as one of the most serious objections to quantum mechanics. It was not settled by theoretical debate. It was settled by experiment, and the experiment did not go the way Einstein expected. Bit 17. The apparatus was built in Paris. Alain Aspect, 1982. He created pairs of entangled photons, sent them flying in opposite directions, and measured their properties at both ends. If Einstein was right and the particles carried hidden instructions, the correlations between measurements would stay below the threshold set by Bell's theorem. If quantum mechanics was right and the connection was genuine, the correlations would exceed it. They exceeded it. The connection was not carried by any signal. It was not traveling at any speed. It was simply there, instantaneous, unaffected by the distance between the particles. Over the next 3 decades, the result was confirmed and refined relentlessly. Every objection was addressed, every loophole closed. In 2015, a team at Delft University ran a version clean enough to settle the question for the foreseeable future. In 2017, a Chinese team used the satellite Michus to test entanglement across 1,200 kilometers of open space. The correlation held. The distance did not weaken it, did not delay it, did not affect it at all. For entangled particles, the space between them is not a barrier. It is not even a factor. Einstein was wrong about this, not about a detail, about the nature of separation itself. 2 particles, 1,200 kilometers apart, behave as though the gap between them carries no weight. As though distance, the thing that defines space, the thing that keeps here and there apart, simply does not apply to them. And this is not a theoretical inference. It is a direct experimental result, replicated across decades, across continents, across every challenge that skeptics could construct. So here's the question that follows. If distance does not affect entangled particles, what is distance? What is space actually doing? Is it the fundamental container we always assumed? Or is it something more like an interface, a surface-level structure that emerges from something deeper? In 2013, 2 physicists followed that thread to a conclusion that, if correct, turns our picture of reality inside out. Bit 18. Juan Maldacena and Leonard Susskind proposed something that sounds abstract until you follow the implication. They conjectured that entanglement and spatial connection are the same thing. Not analogous, not related, identical. Every pair of entangled particles, they argued, is connected by a microscopic bridge in the geometry of space-time. And if this is true, then the relationship between entanglement and space is not what we assumed. Space does not contain entanglement. Entanglement produces space. The connection comes first. The distance comes second. Follow that one step further. If entanglement is what holds space-time together, then removing entanglement does not just weaken the geometry, it destroys it. The regions disconnect. They stop being anywhere relative to each other. Not far apart, not close. The concept of distance between them ceases to apply. This is not a fringe speculation. It builds on the ADS/CFT correspondence, a mathematical framework Maldacena developed in 1997 that has become one of the most intensely studied results in theoretical physics. The framework has been cross-checked in thousands of papers over more than 25 years. It works in certain mathematically controlled settings. Whether it describes our actual universe is still an open question, but the internal math is clean, and what it describes is a reality where 3-dimensional space is not fundamental. It is woven from quantum connections at a deeper level, generated, emergent, like an image on a screen produced by circuitry underneath that you never see. If time is not fundamental and space is not fundamental, then neither of the 2 categories you use to organize every experience you have ever had is bedrock. They are structures built on top of something else, and the question that has been building since the beginning of this film becomes impossible to avoid. What is underneath? What is the thing that time and space are made of? Bat 19. The answer that keeps surfacing from every direction, the one that physicists keep arriving at through completely different paths, is information. Mark van Ramsdonk showed in 2010 that if you start with a quantum system where everything is entangled, and then systematically remove the entanglement, the geometry of space-time stretches and eventually tears apart. At 0 entanglement, Space dissolves into disconnected fragments. The fabric of reality holds together only as long as the quantum connections hold. Remove the connections, and there is no space. What is left is not empty space. It is no space at all. John Archibald Wheeler arrived at the same place from a completely different direction 30 years earlier. In 1990, Wheeler, the man who worked alongside Bohr, coined the term black hole and shaped 20th century physics, proposed a principle he called it from bit. Every physical object, he argued, derives its existence from answers to binary questions. Yes or no, up or down, this or that. A particle does not sit somewhere and then get described by information. The information is what makes the particle. Stack enough binary answers together and you get what looks like an electron, a photon, a gravitational field. Matter does not produce information. Information produces matter. When Wheeler proposed this, most physicists treated it as philosophy. Then the holographic principle appeared. Then ADS/CFT. Then ER equals EPR. Then Van Ramsdonk's result. Each one arrived independently, from a different subfield, using different mathematical tools, and each one pointed at the same conclusion. The foundation of reality is not material. It is informational. Matter, energy, space, and time are all downstream of something more basic. A layer built not from things, but from relationships between bits of data. The pieces were not designed to fit together. They were discovered separately, decades apart, by people who were not looking for a unified picture, and they fit anyway. And if information is the bedrock, it should have physical laws. It should have conservation rules, costs and limits, the way matter and energy do. It turns out it has all three, and each one of them is stranger than the last. Bit 20. The first law of information is the strangest. Information cannot be destroyed. This is not a guideline or an approximation. It is a mathematical property of quantum mechanics called unitarity. The evolution of any quantum system is reversible. If you know the final state, you can in principle reconstruct the initial state. Nothing is lost. Not scrambled beyond recovery, not degraded into noise, preserved, always. The equations do not permit deletion. This is not a feature we chose. It is a feature of the math. It is built into the structure of the most fundamental equation in quantum mechanics, and removing it causes the entire framework to become internally inconsistent. Think about what that means in concrete terms. Burn a book. The pages turn to ash. The ink turns to gas. The words seem to vanish. But according to quantum mechanics, the information on those pages still exists. It is encoded in the exact quantum states of every particle of smoke, every photon of light, every flake of ash that left the fire. In principle, with a complete description of the final state, you could reconstruct every word on every page, not because the book is somehow magically preserved, because the laws of physics do not allow the information to disappear. The universe does not forget. The math forbids it. This is not a philosophical position. It is a structural property of the Schrödinger equation, the most fundamental equation in quantum mechanics. Remove unitarity and the Schrödinger equation breaks. Probabilities stop adding up to 1. The framework that predicts the behavior of every atom in your body becomes inconsistent. Whatever information is, it is permanent in a way that matter is not. A star can be destroyed. A planet can be vaporized. But the information they contained persists, redistributed, scrambled across the quantum states of the debris, but never erased. And if information is conserved like energy is conserved, the next question is whether it is physical like energy is physical, whether it has mass, temperature, cost, whether it obeys thermodynamics. In 1961, a physicist at IBM proved that it does. Bit 21, Rolf Landauer was not thinking about cosmology. He was thinking about computers. Specifically, he was thinking about the minimum cost of computation. And he asked a question that turned out to reach far beyond engineering. What happens physically when you erase one bit of information, not when you smash a hard drive, not when you shred a document, when you erase one bit. A single one flipped to a zero. Landauer worked through the thermodynamics and found a flaw. The act of erasing one bit releases a minimum amount of heat equal to kT times the natural logarithm of 2. K is the Boltzmann constant. T is the temperature of the environment. The number is vanishingly small, but it is not zero, and it cannot be reduced by any means. Not by better materials, not by better engineering, not by any technology that obeys the laws of physics. The universe charges a minimum price for forgetting, and the price is heat. For 50 years, this remained a theoretical result, too small to measure with existing instruments. Then, in 2012, Antoine Béroux and his team at the École Normale Supérieure in Lyon built an experiment delicate enough to test it. They trapped a 2 micrometer silica bead in a laser beam shaped into a double well potential. The bead sat in one well or the other, representing a single bit. They erased the bit by tilting the potential until the bead rolled to one side, and they measured the heat released. It matched Landauer's prediction. 51 years between the calculation and the confirmation. Information is physical. It has a thermodynamic cost. It obeys the same laws as mass and energy. It is not a human invention, not an abstraction, not a convenient label. It is a feature of the universe that was there before we learned to count. And if it is physical and conserved, there is one more question. Is there a limit to how much of it can exist in a given region of space? Bit 22. Yes. And the limit has teeth. Jacob Bekenstein proved in 1981 that the amount of information that could be stored in any finite region of space has a maximum. Not a practical maximum, the kind you hit because your hard drive is full. A fundamental maximum set by the structure of physics itself. The Bekenstein bound says that the information content of a region is limited by its size and the energy it contains. Try to pack more in than the bound allows, and the region does not just overflow, it collapses into a black hole. The universe enforces the limit not with an error message, but with gravitational collapse. Try to write too much data and the storage destroys itself. This is not a corner case or an extreme scenario. It is a direct consequence of general relativity and thermodynamics combined. The limit is real, and the enforcement is physical. Think about what this implies. The universe has a maximum information density, a ceiling on how much can be known, stored, or encoded in any given patch of reality. The ceiling is not negotiable. It is not set by technology. It is set by the relationship between energy, area, and the fundamental constants. Push past it and the geometry itself breaks. The universe treats information capacity the way it treats the speed of light, as a boundary that cannot be crossed, not because of engineering limitations, but because the structure of reality forbids it. Now here is the part that makes this genuinely strange. You would expect the maximum information in a region to depend on its volume. A bigger room should hold more data, the way a bigger hard drive holds more files. But the Bekenstein bound does not scale with volume. It scales with the area of the boundary, the surface, not the inside. When physicists followed this thread, what they found waiting at the end of it was one of the most disorienting results in modern physics. Bit 23. The holographic principle. Gerard at Hooft proposed it in 1993. Leonard Susskind formalized it in 1995, and in 1997, Juan Maldacena provided the mathematical framework through ADS/CFT, the same correspondence that would later underpin ER equals EPR. The principle says that everything happening inside a three-dimensional volume of space can be completely described by information encoded on its two-dimensional boundary. Not approximately, fully. Every particle, every force, every interaction inside the volume has a complete equivalent description living on the surface. The depth of the room does not add information. The walls contain all of it. Sit with that for a moment. You are in a three-dimensional room right now. You move through it freely. Objects sit at different depths. The space around you has height, width, and depth, and all three feel equally real. But the holographic principle says that a complete description of everything in this room, including you, can be encoded on the walls. The third dimension, the depth you perceive when you reach out your hand, is not contributing new information. It is already contained in the two-dimensional surface. Depth, under this framework, is not fundamental. It is derived, computed from what is written on the boundary. This has been studied more intensely than almost any result in theoretical physics over the past 25 years. In the mathematical settings where it can be tested rigorously, ADS/CFT, it holds without contradiction. Whether it applies directly to our universe, which has a different geometry than ADS space, remains an open question. But the structure it reveals is hard to dismiss. The universe stores its data the way a hologram stores an image, not in the bulk, on the surface. So information is conserved, it is physical, it has a cost, it has a maximum density, and that density is governed by surfaces, not volumes. The universe, at its most fundamental level, tracks, limits, and organizes data with the precision of a system that was built to compute. And the question that follows is not whether the universe resembles a computation. It is whether we can measure the difference. Bit 24. The idea that the universe might literally be a computation is older than you would think. In 1969, Konrad Zuse, the German engineer who built the first programmable computer, published a book called Rechnender Raum, Calculating Space. His proposal was blunt. The universe is a cellular automaton. Every point in space is a cell. Every cell updates its state based on the states of its neighbors. The rules are local. The process is discrete. The universe does not flow. It ticks. Zuse was not a physicist. He was the man who built the Z3, the first machine that could execute a stored program. And when he looked at the physical world through the eyes of someone who had spent his life building machines that calculate, what he saw was a machine that calculates. The physics community ignored him. For decades, Rechnender Raum was treated as an interesting overreach by an engineer who wandered too far from his field. Then the holographic principle appeared. Then the Bekenstein bound. Then ER equals EPR. And the sketch that Zuse had drawn in 1969 started looking less like overreach and more like a preview. But if the universe is a computation, it should have a measurable computational history, a total count of operations performed since the beginning. In 2002, Seth Lloyd at MIT calculated exactly that. He used the known mass and age of the universe combined with the Bremermann limit, the maximum rate at which any physical system of a given mass can process information, and arrived at a specific number. Roughly 10 to the 122nd power operations since the Big Bang. Not infinite, not unknowable, finite and countable. The universe, if it is computing, has a clock, and the clock has ticked a specific number of times. We know the number. That changes the shape of the question. It is no longer about whether the universe resembles a computer. It is about whether we can test the difference between a universe that computes and one that does not. Bit 25. Can we test this? Can we actually distinguish a universe that computes from one that does not? 3 physicists at the University of Washington proposed a way in 2012. Silas Bean, Zoe Davudi, and Martin Savage asked what the universe would look like if it were running on a lattice, a grid with a finite smaller step, the way a simulation runs on a discrete mesh. Their reasoning was straightforward. If the grid exists, it should leave fingerprints. Cosmic rays at the very highest energies should behave slightly differently depending on which direction they travel, because the lattice has axes, and particles moving along those axes would experience the grid differently than particles moving diagonally across it. This is a concrete, testable prediction. You build a detector. You collect ultra-high energy cosmic rays. You look at the distribution of arrival directions and energies. If there is a lattice, you see anisotropy, a directional bias that should not exist if space is continuous. If there is no lattice, the distribution is smooth. The data so far is not conclusive. The energies involved are at the extreme edge of what current detectors can capture. And the statistical sample is small. But that is not the point. The point is that the method exists. The question has left philosophy and entered the domain of experimental physics. Whether reality is computed or continuous can, in principle, be resolved by data. And that alone changes its status from speculation to science. But here is where I want to step back for a moment and be honest about what we have established and what we have not. We have seen that time is not fundamental. That space may not be fundamental. That information behaves like a physical quantity with conservation laws, costs, and limits. That the structure of reality, at the deepest level we can probe, looks more like an information system than a material one. These are real results from real physics, published in real journals, checked by real peers. What we have not established is what this means. The universe could be a computation. It could also be something else entirely that merely has computational properties. The math does not settle the question. It may never settle it, and it is important to hold that honesty, because the next place we are going is the place where even the math stops working. What the math does settle with uncomfortable clarity is that the two theories we rely on to describe reality cannot both be right. And the place where they collide is the smallest scale that physics can define. Bit 26. Below everything we have described, beneath the information and the entanglement and the emergent geometry, lies a scale so small that the laws of physics themselves stop giving coherent answers. The Planck length, 10 to the minus 35 meters. The Planck time, 10 to the minus 43 seconds. These numbers are not chosen. They are calculated from three fundamental constants: the speed of light, the gravitational constant, and Planck's constant. And they mark the scale at which the known laws of physics stop producing meaningful answers. Not because our instruments are too crude, because the math itself breaks. At distances shorter than the Planck length, the equations we use to describe space and time return nonsense. Infinities, contradictions, outputs that have no physical interpretation. And there is a deeper reason for this, one that is worth sitting with. To measure something at a given scale, you need a probe with energy high enough to resolve that scale. The smaller the thing you want to see, the more energy you need. At the Planck scale, the energy required to resolve the distance is so high that it warps space-time at the point of measurement and creates a black hole. The act of looking destroys the thing you are looking at. You cannot peer below the Planck length because the instrument collapses the target. This is not a technological limitation. It is a structural one. The universe does not just fail to answer questions below this scale, it prevents you from asking them. And here is why this matters for everything we have been building toward. The Planck scale is exactly where our two best theories meet. General relativity, which describes gravity and the large-scale geometry of the cosmos, and quantum mechanics, which describes particles and forces at the smallest scales. Both have been tested for over a century. Both work with extraordinary precision in their own domains. And at the Planck scale, they collide. General relativity says space is smooth and continuous. Quantum mechanics says that at small enough scales, everything fluctuates. At the Planck scale, these two descriptions do not merge. They contradict. And the contradiction has been open for 90 years. Bit 27. Quantum field theory learned to live with its own infinities. It has a procedure for this, and the procedure is one of the most successful and most uncomfortable things in all of science. When you calculate how particles interact using quantum field theory, the equations produce infinities at almost every step. The self-energy of an electron comes out infinite. Basic scattering probabilities come out infinite. The raw mathematics is in a strict sense broken. Renormalization fixes this by introducing a cutoff. You tell the equations to ignore contributions above a certain energy, and then you absorb the remaining infinities into the definitions of the physical constants. You redefine the mass and charge of the electron to include the infinite corrections, so that the measured values come out finite. It works. The prediction of the electron's anomalous magnetic moment, calculated through this procedure, matches the measured value to 12 significant figures. That is the most precise agreement between a theoretical prediction and an experimental measurement that exists anywhere in science. And Richard Feynman, one of the architects of the procedure, called it sweeping the dirt under the rug. He acknowledged that it worked. He acknowledged that it gave correct answers, but he also said that subtracting infinity from infinity to get a finite result is not, in any rigorous sense, legitimate mathematics. It is a trick that has never once given a wrong answer, but still a trick. Now here is the fracture. Renormalization works for 3 of the 4 fundamental forces: electromagnetism, the weak force, the strong force. All 3 can be renormalized. The infinities are absorbed, the predictions come out finite, and the numbers match experiment. But when you try to apply the same procedure to gravity, it fails. The infinities do not go away, they multiply. Each level of approximation introduces new types of infinity that cannot be absorbed into existing constants. The technique that saves 3 forces breaks on the 4th. And the 4th force is the one that shapes the large-scale structure of the universe. Bit 28. So we have 2 descriptions of reality. General relativity handles the large: stars, galaxies, the curvature of space-time, the expansion of the cosmos. Quantum mechanics handles the small: atoms, particles, forces, the behavior of matter at distances where classical physics stops working. Both have been tested beyond any reasonable doubt. GPS satellites depend on general relativity. Every transistor in every chip in every phone depends on quantum mechanics. These are not tentative models. They are the most thoroughly verified descriptions of nature that human beings have ever produced. And they do not fit together. Not because we have not tried, not because we lack talent or data or computing power. Because the things they say about reality at the most basic level are incompatible. General relativity describes a smooth, continuous, deterministic space-time. Quantum mechanics describes a grainy, probabilistic, uncertain substrate. They do not disagree about details. They disagree about what the world is made of and how it behaves. General relativity says gravity is geometry, the curvature of a smooth fabric. Quantum mechanics says every force is carried by particles exchanged between other particles. You cannot have both at the same time. Smooth geometry and particle exchange are different languages with different grammars, and no one has found a way to translate between them without the math collapsing. For 90 years, physicists have tried to reconcile them. Loop quantum gravity, causal set theory, asymptotic safety, twistor theory. Each one is an attempt to find the deeper structure that both theories are approximations of. None has produced a complete, experimentally testable framework. The gap remains open. And in 1984, a theory arrived that claimed it could close the gap permanently. It promised one equation for everything. One framework that would produce all particles, all forces, all of physics from a single mathematical structure. The promise was so large and so confident that an entire generation of theoretical physicists reorganized. They are tiny vibrating strings, unimaginably smaller than an atom, and different modes of vibration produce different particles, the way different frequencies on a guitar string produce different notes. One vibration gives you an electron, another gives you a photon, another gives you a quark, and crucially, one mode gives you the graviton, the hypothetical carrier of gravity that every previous attempt to construct had failed to produce. Everything in the universe, every force, every particle, every interaction, from a single object vibrating in different ways. Edward Witten, widely regarded as the most brilliant mathematical physicist of his generation, called string theory a piece of 21st century physics that fell into the 20th century by accident. In 1995, he unified 5 competing versions into a single framework called M-theory. The physics community did not just pay attention, it reorganized. Departments shifted focus, funding flowed. Hundreds of theorists redirected their research. Graduate students were steered towards strings as the most promising path in fundamental physics. For many in the field, this was not just a promising idea. This was the answer. The framework that would finally close the gap that had been open since Einstein and Bohr. That was 40 years ago. And what happened in those 40 years is one of the most quietly devastating stories in modern science. Bit 30. String theory did not produce one universe. By the early 2000s, it became clear that the equations allowed not a single solution, but a landscape of roughly 10 to the 500th power possible solutions. Each one corresponds to a different set of physical constants, a different menu of particles, a different version of physics. Raphael Bousso and Joseph Polchinski laid this out in 2000. Leonard Susskind formalized it in 2003. Our universe, with its particular constants and its particular particles, is one point in this landscape. One possibility among a number so large it dwarfs every quantity in astronomy. Every count of atoms. Every measurement ever made. There is no mechanism inside the theory that selects our universe. No equation picks our constants. No principle explains why we are here and not somewhere else in the landscape. The theory that was built to derive the constants of nature from first principles instead produced a catalogue of all possible constants with no way to choose between them. Here is what that means, and it is worth being precise about it. String theory was designed to answer why the electron mass is what it is, why the forces have the strengths they have, why there are 3 families of matter. The answer it gives is, all values are possible, and ours is one of them. That is not an answer to the question. It is an abandonment of the question. A theory that accommodates every possible outcome has no power to explain any particular outcome. Susskind proposed that this was not a failure, but a feature. He argued that all 10 to the 500th universes actually exist, each one a bubble in an eternally inflating multiverse, and we simply find ourselves in the one compatible with our existence. This is the anthropic landscape, and it leads back to the same dead end we reached with fine-tuning, an unfalsifiable framework that explains all observations by predicting all possible observations. Bit 31. For 2 decades, the doubts stayed mostly private. Then, in 2006, they became public. Peter Voigt, a mathematician at Columbia, published Not Even Wrong, a title borrowed from a phrase Wolfgang Pauli used to describe ideas too vague to be tested. Voigt's argument was specific. 40 years of work on string theory had not produced a single, unique, testable prediction. The energies at which the theory makes distinctive predictions are near the Planck scale, which would require an accelerator the size of a galaxy to probe. No experiment currently conceivable can confirm or refute it. Lee Smolin, a theoretical physicist at the Perimeter Institute, published The Trouble with Physics the same year. His concern was broader. He argued that the dominance of string theory had distorted the field itself. A generation of the most talented young theorists had been channeled into a research program that could not make contact with experiment, while alternative approaches to quantum gravity were starved of funding and attention. These are not fringe complaints. They point at a genuine problem in the logic of science. A theory that cannot be tested against nature, no matter how mathematically beautiful or internally consistent, does not qualify as a scientific theory in the operational sense. It qualifies as a mathematical structure. And after 4 decades, string theory has not crossed the line from one to the other. But the situation has gotten stranger since. In 2005, Qumran Vafa at Harvard launched the Swampland program, an effort to determine which of the 10 to the 500th solutions are physically viable and which are mathematical ghosts. In 2018, Obied, Ugari, Spodinico, and Vafa published a conjecture that shook the field. It said that in any universe consistent with string theory, the cosmological constant cannot be positive and static. It must change over time. But every measurement we have of the cosmological constant is consistent with it being positive and static. The thing that makes up 68% of the universe behaves, as far as our instruments can tell, exactly the way a fixed constant would behave. And the swampland conjecture says a fixed constant is not allowed. Think about what that means. The most developed attempt to unify physics spent 40 years unable to make a testable prediction. And the one internal constraint it has produced appears to contradict the most prominent feature of the observed universe. The theory built to explain reality may be structurally incompatible with reality, and we are left standing in the same place we started, with equations that work and a foundation that does not explain itself. But there is one more layer, one more place where the floor thins out, and it involves something that makes up 85% of all the matter that exists. Bit 32. The galaxies were moving too fast. That was what Fritz Zwicky saw in 1933 when he measured the speeds of galaxies inside a structure called the Coma Cluster, about 320 million light-years away. He used the Doppler shift of their light to calculate how fast they were moving, and then he compared those speeds to the amount of visible matter in the cluster. The numbers did not balance. The galaxies were moving far too fast. At the velocities he measured, the gravitational pull of everything visible, every star, every cloud of gas, was not nearly strong enough to hold the cluster together. It should have blown apart billions of years ago. Every galaxy in it should have escaped into intergalactic space long before Zwicky ever pointed a telescope at it. But it had not. The cluster was there, intact, bound, held together by something Zwicky could calculate but could not see. He did the math carefully. To account for the observed speeds, the cluster needed roughly 10 times more mass than the visible matter contained. And this mass was not hiding behind something. It was not obscured by gas or dust. It was not emitting any light, not absorbing any light, not interacting with light at all. It was gravitationally present and electromagnetically invisible. Zwicky gave it a name: Dunkel Materie, dark matter. The physics community did not take him seriously. Zwicky was brilliant but impossible to work with. He insulted colleagues in public, called other astronomers spherical bastards, meaning they were bastards from every angle, and accumulated enemies the way other scientists accumulate citations. His personality made it easy for the field to set his result aside rather than confront what it implied. And the claim sounded too large. Most of the matter in the universe is invisible. That is not the kind of statement the scientific establishment absorbs easily, even when the data supports it, even when the math is clean. The result was noted, filed, and left alone for 40 years. It took someone else entirely, working on a different problem with different instruments in a different decade, to show that Zwicky had been right all along. Bit 33. Vera Rubin spent years being told she did not belong. She was discouraged from applying to Princeton because the graduate astronomy program did not accept women. She was steered away from cosmology for her thesis because it was considered too ambitious for someone in her position. She was not invited to use certain telescopes because the facilities did not have women's restrooms. She chose to study the rotation of galaxies instead, a topic considered safe and unglamorous. And what she found in that quiet corner of astronomy turned out to be more consequential than almost anything the people who tried to redirect her ever produced. In the 1970s, working with Kent Ford, Rubin measured the rotation speeds of stars at different distances from the centers of spiral galaxies. The expectation was straightforward. Stars close to the center, where most of the visible mass sits, should orbit fast. Stars further out, where the visible matter thins, should orbit slower. This is how orbital mechanics works. It is why Mercury moves faster than Neptune. The closer you are to the mass, the faster you go. The stars did not slow down. The rotation curves came back flat. Stars at the far edges of galaxies were orbiting just as fast as stars near the center. This was not possible if the visible matter was all there was. Either the law of gravity was wrong at galactic scales, or these galaxies contained far more mass than the light revealed. Mass that did not glow. Mass that did not interact with any telescope ever built. Mass that was there, shaping the orbits, holding the structure together, and completely invisible. Rubin's data confirmed what Zwicky had seen 40 years earlier from a completely different direction, and this time, the evidence could not be shelved. It came from dozens of galaxies, measured independently, with flat rotation curves in every single one, not just in one type of galaxy, in spirals, in dwarfs, in barred spirals. Everywhere Rubin looked, the same pattern. The invisible mass was not a quirk of one cluster. It was everywhere. Roughly 85% of all the matter in the universe is something we cannot see and have never directly detected. The search for what it actually is has now been running for half a century, and the results of that search are difficult to look at. Bit 34. The leading hypothesis for decades was a particle. A heavy, stable particle that interacts through gravity and the weak nuclear force, but not through electromagnetism. Physicists called these WIMPs, weakly interacting massive particles. The logic was clean. If dark matter is made of WIMPs, they should occasionally collide with ordinary nuclei, producing a faint signal in a sufficiently sensitive detector. Build the detector large enough, shield it deep enough underground to filter out cosmic ray noise, wait long enough, and you should see them. So we built the detectors. Lux, a vat of ultra-pure liquid xenon in a mine in South Dakota. Xenon 1T and then Xenon NT, larger and more sensitive versions under a mountain in Italy. Panda X, in a laboratory carved into marble in China. Each generation more sensitive than the last by a factor of 10 or more. Each one designed to catch the faintest possible signal from a particle that barely interacts with anything. The results came back. Nothing. Lux ran from 2013 to 2016. No signal. Xenon 1T reported in 2018. No signal. Xenon NT continues to run. No signal so far. Panda X, same result. Each detector pushed the sensitivity threshold lower, excluded more of the parameter space where WIMPs could be hiding, and found nothing. Meanwhile, the Large Hadron Collider, the most powerful particle accelerator ever built, has been searching for supersymmetric particles, the theoretical relatives of WIMPs predicted by extensions of the standard model. 3 runs, billions of collisions, not one supersymmetric particle found. The Axion, another dark matter candidate, has been hunted by the ADMX experiment. Nothing so far. 50 years of searching, 3 generations of detectors, billions of dollars, entire careers spent listening for a whisper that never came, and the count of confirmed dark matter particles stands exactly where it stood when Zwicky first noticed the problem in 1933, at 0, bit 35. There is an alternative, and it deserves an honest hearing. In 1983, Mordechai Milgram, an Israeli physicist, proposed that the problem might not be missing matter at all. Maybe everything we see is everything there is. Maybe what needs fixing is not the inventory of the universe, but the law of gravity itself. Milgram's idea was specific. At very low accelerations, the kind that dominate at the outskirts of galaxies, gravity does not follow Newton's inverse square law exactly. It falls off more slowly. Plug this modification into the equations, and the flat rotation curves that Rubin measured appear naturally. No dark matter required. No invisible particles. Just a small correction to gravity at a scale we had never tested directly. The idea is called MOND, Modified Newtonian Dynamics, and it works better than it should. It predicts the rotation curves of spiral galaxies with remarkable accuracy, including galaxies it was never designed to fit. Stacy McGaw at Case Western Reserve has documented this extensively. In some cases, MOND matches the data more tightly than the standard dark matter model. But MOND has its own failures. It cannot account for the behavior of galaxy clusters, the same structures that led Zwicky to propose dark matter in the first place. It struggles with the cosmic microwave background, the faint glow from the early universe whose fine structure the standard model predicts with extraordinary precision. And it lacks a widely accepted relativistic version, a formulation that works within the framework of general relativity rather than alongside it. So here is where this leaves us. Two models. One says 85% of the matter in the universe is invisible and made of particles nobody has found, despite 50 years of searching with increasingly powerful instruments. The other says gravity behaves differently than we thought at scales we have not fully tested. Neither one explains everything. Neither one can be ruled out. And between them, the most basic question you can ask about the physical world: what is this made of? What holds it together? What is the stuff beneath the stuff? Does not have an answer. Bit 36. We started at the surface, the floor holds, the lights come on, the equations predict and the predictions land. Physics works. That was the starting point, and it was not wrong. The surface is solid, the machinery runs, and then we went underneath, layer by layer, and every layer we opened was thinner than the one above it. The expansion of the universe is accelerating, and nobody knows why. The equations that should describe it disagree with each other by a number with more zeros than there are atoms in the cosmos. The constants that hold reality together are not derived from any theory. They are measured and entered by hand, and their margins are so tight that stepping outside any one of them produces a universe with nothing in it. One physicist predicted a nuclear resonance from the mere fact that carbon exists and found it exactly where the logic said it must be, and spent the rest of his life unable to explain why the logic worked. At the quantum scale, reality does not settle into a definite state until something forces it to, and the choice of when to force it can be made after the event has already occurred. 100 years of effort to explain this has produced 15 competing pictures, all giving the same predictions, none distinguishable by experiment. The world is not both local and real, and we do not know which one to give up. Time moves forward because of an initial condition so improbable that the number describing its improbability is larger than the universe. Space may not be fundamental. It may be stitched together from quantum connections that, if severed, cause the geometry to dissolve. Information appears to be the deepest layer, physical, conserved, limited, stored on surfaces rather than in volumes. And the two theories that describe reality with extraordinary precision in their own domains cannot be combined without collapsing into infinities that no mathematical trick can absorb. The best attempt to unify them produced not one answer, but 10 to the 500th, and in 40 years has not generated a single testable prediction. Its own internal constraints may rule out the universe we live in, and 85% of the matter that holds everything together has never been seen. We started by saying, the floor holds. It does. The surface is solid, but underneath it, at every level, the supports are either missing, contradictory, or unexplained. The equations work, and the thing they rest on is something that, after a century of the most intense scientific effort in human history, no one can describe. Bit 37. And yet, here you are, sitting on that floor, inside that gap, made of atoms that should not exist in a universe this finely tuned, experiencing time that has no reason to flow the way it flows, held together by forces that work perfectly and explain nothing about themselves. Every equation that describes you lands. None of them predicted you, and none of them can say why you are here rather than not. But you are not an equation. You are the part of this that woke up. The part that looked around, noticed the cracks, and asked what was underneath. In a cosmos this old, this large, this full of silence and unanswered questions, something exists that refuses to stop looking. Something that builds detectors, fires single electrons through slits one at a time, measures the heat released by the erasure of a single bit, and stares at the rotation curves of galaxies until the data gives up its secret. Not because it was told to, because it wanted to know. Whatever is behind the wall, whatever holds the equations together from underneath, whatever the floor rests on, you are the thing that noticed it was there. And in a universe that cannot explain its own foundations, that might be the most unreasonable thing of all.